In this video, I'm going to go through a few examples of how parabolas are treated on the IB exam, so we're just going to get right into those. So the first example, the diagram below shows y equals 5 minus x times x plus 3, with a and c being x-intercepts and b being a maximum point. Find the coordinates of points a, b, and c. So any of the problems in this video that you feel comfortable doing on your own, pause the video, do as much as you can on your own, and then just sort of check back with me to make sure that you've got them right. So the first thing we see is that the question is asking for the coordinates of a, b, and c. I'm going to go ahead and start with the x-intercepts, with a and with c. So I know that a and c can be found as x-intercepts by letting y be 0 and solving for x. So if I set y to be 0, if I let y equal 0, I'll have 0 equals 5 minus x times 3 plus x. And if I solve these, I'm going to end up with x being 5 and with x being negative 3. That sort of leads me to the idea then that the point A is most likely negative 3, 0, and C is the point 5, 0. So already we found point A and we found point C. So next, we need to find B. And B is the vertex. And I mentioned in the previous video that when you have an equation that's been given to you in intercept form, once you have the two x-intercepts, you can find the x-coordinate of the vertex by taking the average value of the two sort of x-coordinates of the x-intercepts, right? So I'm going to use x equals negative 3 plus 5 divided by 2. I'm just averaging together the negative 3 and the 5. That'll give me 2 over 2, which is 1. So that tells me that coordinate B is 1, comma, something. I just have to find the y-coordinate. To find the y-coordinate, I'm just going to evaluate my original quadratic equation using x as 1. So I'll have y equals 5 minus 1 times 3 plus 1. That's going to give me 4 times 4, which is 16. So that B point is 1, 16. So we found A, we found B, and we found C. These problems are really straightforward. And like I said, all three of these problems are direct modifications of IB questions. These have the chance to be very simple questions, but we need to make sure that we get them right and that we get them right quickly. Okay, so in this next example, part of the graph of y equals d times x minus m squared plus p is given below. The x-intercepts are 1, 0, and 7, 0. The vertex is m, 3. They want me to write down the values of m and p and find the value of d. Okay? So we sort of start by reading the question. The first thing they ask us to do is they ask us to write down, and by the way, when they say write down on the IB exam, it generally means it's not going to take you any work, just write them down, right? So they're going to write down the values of m and p. So where are m and p? Well, m is right here and also there, and p is here at the end, right? So m is the x-coordinate of the vertex, right? How can we find the x-coordinate of the vertex? Well, once again, they were kind enough to give us the two x-intercepts, 1 and 7, and so we know that the x-coordinate of our vertex should be the average of those, 1 plus 7 over 2, which gives me 4, right? So right away, I can tell that m is going to be 4, right? So we found one of those things. Okay. Next up, p, right? So we know this point here is 4, 3. Well, given that this equation was given to us in vertex form, we can tell that p should be the y-coordinate of the vertex. That tells me that p should be 3. Okay. Now, something that's valuable to do as you're going through these problems is as you're finding these values, use them to refine your equation. At this point, we know that our equation is y equals d times x minus not m anymore, but 4 squared plus not p anymore, but 3. Like, this is my equation. This is what I've been working with all along. And you might as well sort of focus on that idea. So now that we're done with part A, we can go on to part B, right? How can I find the value of D? How can I figure out what D is? I mean, I'd like you to pause the video for a minute and think about this. Should be a simple thing, but just make sure you've got some idea of it. The idea is this equation should be true for any point on the graph. So if I take any point that I have here, any point that I know about, 1, 0, 7, 0, or 4, 3, and use them here, we should be able to figure out what D is, right? It occurs to me now, using the vertex isn't a good idea because it'll turn this into 0 and d will disappear, but if we pick either of these, we should be in good shape, right? So I'm going to pick the point 1, 0. It means that 0 should be equal to d times 1 minus 4 squared plus 3. And notice I now have an equation where I can just solve for d. This should be really, really simple, right? I'll have negative 3 equals d times negative 3 squared is 9. That's going to give me d equals negative 1/3. Right? So there's my answer for part B. Right? Again, fairly straightforward problems, but we need to have exposure to them and we need to be able to get through them really quickly. And one last example for us to work through, and I really want to make sure that A gets a chance to make sense. Because in A, they're asking us to express this standard form equation in vertex form instead. And in my opinion, there are two ways to do that. One of them is by completing the square. And the second is by being sneaky. And I'll show you both of those, but I want to start with completing the square. Completing the square is something that you saw back in intermediate algebra and may not have used since then. So I'm going to walk through what that process looks like. What we do is we take our original equation, and generally I'll move the 23 to the other side so that it's sort of out of the way. The other thing you're going to need to do is you're going to need to factor anything that's in front of that x squared out. And you're going to notice that I'm going to leave this sort of conspicuous blank space where the completed square needs to go. The next thing that you may remember from your intermediate algebra days is that once this 2 has been factored out, we take half of this middle term and square it. So we get plus 9 here. But to be fair to this equation, I have to put something to balance on the other side of this equation. And it's not just plus 9. It's this plus 9 times 2. So we actually have to add 18 over here. So that gets me y minus 5 equals 2 times, now the whole point of doing this is so that it will be written as a completed square. I can write it as x minus 3 squared. From there, my next step is just to move the 5 back over, and I get y equals 2 times x minus 3 squared. Kind of an ugly x, but we'll deal with it, plus 5. And there we go, yay, we did part A. Now, the sneaky method. Right? Completing the square is great. I love it. But the sneaky method is just kind of neat. What I mean by the sneaky method is basically all we really need to know is the vertex. If I can find the vertex, I can use that to build vertex form, because that's all this is. This is basically just vertex form. So how can I get the vertex out of this thing? Well, we could use x equals negative b over 2a. In this problem, that would be 12 over 4, which means the x-coordinate is 3. How would I find the y-coordinate? Well, y would be equal to 2 times 3 squared minus 12 times 3 plus 23. And if we solve this out, we shouldn't be surprised to find out that it turns out to be 5. Now, how is that helpful? Well, we know that vertex form, and I'm actually going to move that off the top of the screen, we know that vertex form is supposed to be y equals some constant in the front, and I'll have to ignore that for a second. So some constant times x minus the x-coordinate of the vertex, which is 3 squared, plus the y-coordinate of the vertex. 2 kind of got messed up. The y-coordinate of the vertex for us is 5. All we need is the a value that goes in front, but remember that this a value right here is supposed to be the same as whatever the a value is in the original thing. That means it's going to be 2. And notice that we were able to get the exact same vertex form without going through completing the square. Again, completing the square is a great tactic, it's a great thing for us to know about, but it's also valuable for us to know that if you can get the vertex, just write it in vertex form. Like all we need to do is get that thing. Okay? So the next part of this problem, part B of this problem, is saying that x squared can be transformed into this thing by a series of transformations. By a stretch with factor k, a horizontal translation of p units, and a vertical translation of q units. This problem is just asking us to write down the values of these constants. So, again, write down generally means that they don't expect you to be doing a lot of work. They expect you to just sort of be looking at the things and understanding what they are, right? So what is the vertical stretch scale factor? Well, this k is going to be 2. That's the number in the front that's sort of scaling vertically how large this thing is. Next up is a horizontal translation of p units. So what is the horizontal translation? Well, this thing is sort of translated by 3 units horizontally, right? That's this, if you think about what these things do, this one is effectively the x-coordinate of the vertex, so it's how far the graph is shifted or translated to the right. The d at the end is how far the graph is shifted or translated vertically. And so that leads me quickly to the idea that q is just the number that's added on the end, which we found to be 5. Okay? And that's it for this problem. So you'll notice, I really don't believe that these problems are complicated and challenging. They're just problems where they're asking you to have a solid knowledge and understanding of all the different forms and what you can do with them.